Hello class 10. We are discussing the topic calorimetry, wherein we started with first of all the concept of heat. We discussed the units of heat, joule, calorie, the units of heat, their definitions, and then after we looked at the concept of temperature, the units of temperature, Kelvin, Celsius, there's Fahrenheit also. Basically here we are only going to talk about Kelvin and Celsius. This is the relationship between the two units. And another, then after, very important thing, which is the factors affecting the quantity of heat gained or given out by your body. There are three factors, which are, first of all, the heat gained or given out by your body is dependent on the mass of the body. In fact, we saw that the heat given out is directly proportional to the mass. Heat received or given out is directly proportional to the mass. Then after, the second factor is the rise in temperature. The more the rise in temperature, the more heat is received by the body. And the third factor is the nature of the body. Nature of the body meaning good conductors or bad conductors. So from these three factors, we jump at the concept of thermal or heat capacity. Of course, before this we looked at the distinction or differences between heat and temperature. Then after we spoke about, like I said earlier, heat capacity or thermal capacity, denoted by a capital C, which is this relation Q by delta T, which is the amount of heat received by a body to raise its temperature by unit degree. That is the definition for heat capacity. This is the relation. Call it C dash or capital C simply will do. I believe we had used capital C, which is Q by delta T. And the unit for heat capacity is joule per Kelvin or joule per degree C, as you can see. Joule per Kelvin or joule per degree C. You can get it from this relation itself. Then we spoke about a very important concept, which is the specific heat capacity, the concept of specific heat capacity. Specific heat capacity is denoted by a small c, and the relation is Q by M delta T. Its definition is, you can learn the definition from the relation itself, which is the quantity of heat required to raise the temperature of unit mass of a substance by unit degree. That is the definition for specific heat capacity. What about the units? Units is joule per kilogram per Kelvin. That is the SI unit. Okay, you can use another unit also, which is joule per kilogram per degree C. Alright, so that is the relationship for specific heat capacity. You can refer to my earlier videos also to understand specific heat capacity. Then after, the distinction between heat capacity and specific heat capacity also we have already dealt with. Now today what we are going to discuss is, we are going to discuss something called a calorimeter. A calorimeter is a copper vessel, okay, which is cylindrical of course in shape, which is used to measure the amount of heat gained or lost by a body when it is mixed with another body. So basically here is the picture. It is a copper vessel. So this black line denotes the copper vessel. This copper vessel is enclosed by a wooden jacket. So you have an outer covering which envelopes this, a copper vessel. So this outside wall is that of the wooden jacket, as you can see written. So this is the copper vessel, this is the wooden jacket. Now the space between the wooden jacket and the copper vessel is filled up by an insulator, basically wool or cotton. And you have a wooden lid covering up the copper vessel, or so to say the calorimeter. Now this wooden lid has two holes. Through one of the holes you have a stirrer passing, and through the other hole you have a thermometer passing. So basically this is what a calorimeter is made up of. You have a copper vessel. The copper vessel is enclosed by a wooden jacket or wooden covering. The space between wooden jacket and calorimeter is filled up by some insulator, basically wool or cotton. The calorimeter has a wooden lid. The wooden lid has two holes. Through one of the holes you have the stirrer passing, which stirs, or which mixes the two bodies, so to say, two liquids basically. And you have a thermometer passing through the other hole. So this is the basic, this is what calorimeter basically is made up of. Now there is one famous question that you will be asked, okay, why do we choose copper, to make up a calorimeter? Now we use copper to make up a calorimeter because copper is a good conductor of heat. Okay, so the vessel, that is the copper vessel, readily acquires the temperature of its contents. Okay, so that is one of the reasons. And the other reason is copper has low specific heat capacity, so that just by gaining a very small amount of heat, it readily acquires the temperature of its mixture, of its contents, so to say. Okay, so these two basically are one and the same reason actually, because any good conductor of heat will have low specific heat capacity, remember. So if you are asked why do we choose copper to make up a calorimeter, you have to give these two reasons. That will fetch you 2 marks, remember. Next, see, we don't want the heat from inside the calorimeter to be lost to the surroundings. We want the heat from inside the calorimeter to remain inside the calorimeter. Okay, now heat can be lost in 3 ways, that is conduction, convection and radiation. So in order to minimize the heat lost by radiation, what we do is we polish the inner and outer surfaces of the copper vessel. So the inner and outer walls of this copper vessel, it's highly polished, so that we can minimize the heat loss due to radiation. Then after, the space between the wooden jacket and the copper vessel, like we've already discussed, is filled up with some insulator, wool or cotton, so that there is no loss of heat from inside the container, from inside the copper vessel to the surroundings by conduction. There is no heat loss by conduction. So to minimize heat loss by conduction, the space between the wooden jacket and the copper vessel is filled up with an insulator. And finally, we have this wooden lid, wooden covering up the calorimeter, so that there is no loss of heat by convection. So to avoid heat loss by convection, we have the wooden lid covering up the calorimeter. So this is all that you need to know about a calorimeter. First of all, how a calorimeter is made, okay, this picture. Then after, what is the use, why do we use a copper vessel to make up a calorimeter? Then after, the 2 reasons that we gave, it is a conductor, good conductor, it has low specific heat capacity. Then after, how do we minimize heat loss by radiation? By polishing the inner and outer surfaces of the copper. Heat loss by conduction is reduced by using an insulator between the wooden jacket and the copper vessel. Heat lost by convection is reduced by using a wooden lid, do not forget. Then, very, very important, we talk about the principle of mixtures, or also called the principle of calorimetry. Now, what is this principle of calorimetry? This thing tells us that whenever we mix a hot body to a cold body, or whenever we bring a hot body and a cold body in contact, so what happens is there is transfer of heat that takes place. Transfer of heat between the hot body and the cold body. What basically happens is the heat from the hot body starts flowing towards the cold body. Now, when we consider, if there is no heat loss to the surroundings, that is, this is an ideal scenario, by the way, because whenever we bring a hot body in contact with a cold body, there is always heat loss to the surrounding. But if we do not consider any heat loss to the surrounding, then what we can say, whatever is the heat lost by the hot body is gained by the cold body. So that is what is basically called a principle of mixtures or principle of calorimetry. So if we consider heat loss to the surroundings to be negligible, then heat energy lost by the hot body is equal to heat energy gained by the cold body. This is what is called a principle of mixtures or principle of calorimetry, a very important thing. Now, based on this, we are going to do numericals in this particular chapter. And do remember, for all numericals, we will consider the heat loss to the surrounding to be negligible. We consider there is no heat loss to the surroundings, such that heat lost by the hot body is equal to heat gained by the cold body. So, let us look at a use of this over here. So, if we have two substances A and B, so A has mass M1, specific heat capacity C1, and A is at a higher temperature T1. Now B has mass M2, specific heat capacity is different, which is C2, and it is at a lower temperature T2. So B is the colder body and A is the hotter body. Say they are liquids. Now what we do is we mix them together. Now when we mix them together, A will lose heat and B will gain heat, of course. Thereby what happens is the mixture of these two substances A and B will reach a final temperature. The final temperature, say, is T. Now obviously remember, T will be lesser than T1 and T will be greater than T2. The final temperature T will be greater than the temperature of B, initial temperature of B, and the final temperature T will be lesser than the initial temperature of A, which is T1. So what is the fall in temperature of substance A? It is T1 minus T. So the loss in temperature of A will be T1 minus T. Rise in temperature of B will be T minus T2, the final temperature minus initial temperature. So what is the heat lost by A? Heat lost by A will be, we know Q is MC delta T. Okay, we get this expression from the factors affecting heat lost or gained by a body. Okay, so heat energy lost by A will be its mass into its specific heat capacity into the change in temperature. In case of A, it is the fall in temperature. So M1 C1 delta T is this much in case of A, the fall in temperature, which is this much, T1 minus T. Likewise, heat energy gained by B will be M2 C2 into the change in temperature for B or the rise in temperature for B, which is T minus T2. So this much is the heat gained by B. This much is the heat lost by A. So using principle of mixtures, if we consider no heat loss to the surroundings, then heat energy lost by A has to be equal to heat energy gained by B. So therefore we have this heat energy lost by A, which is the left hand side, is equal to heat energy gained by B, which is your right hand side, remember. So using this, that is the principle of calorimetry, these kind of expressions, we are going to solve numericals. Now there are some consequences of high specific heat capacity of water. Water is one substance which has a very high specific heat capacity, which is 4200 joule per kilogram per Kelvin. Water has high specific heat capacity of 4200 joule per 4200 joule per kilogram per Kelvin. So this is the value of high specific capacity of water. That is, if we have 1 kilogram of water, then to raise the temperature of 1 kilogram of water by 1 Kelvin or 1 degree Celsius, so to say, we have to give 4200 joules of heat energy. So that's a very high value of heat energy, remember. So there are some consequences of high specific capacity of water. You have to give these things a look. That is, the climate near the seashore is moderate. We have sea breeze and land breeze. The phenomenon of sea breeze and land breeze you have studied about happens because of high specific heat capacity of water. Because in the coastal areas, land gets heated up faster than ocean water or sea water, and likewise land gets cooled up faster than ocean water. That is why, because of that, we get land breeze and sea breeze. So that is one of the consequences of high specific heat capacity of water. Hot water bottles are used for fermentation. Fermentation meaning we use warm water in bottles or hot water in glass bottles during winters. Okay, so that is used for that is what is called fermentation. That, you know, hot water bottles also helps to relieve pain, like we use, you know, hot water bag. That is the exact purpose